So we'll start within 3 to 4 minutes, right? So I hope I am audible, right? Hello. Is my voice audible? Hello. So if I am audible, any one of you just confirm. Hello. If I am not getting any response from your side, so if I am audible, just any one of you
Sir,
unmute
audible,
and
sir.
yes.
Sir, audible.
Yes, yes, audible, sir.
Okay, so in this week, welcome to the week 11 of the live sessions on the Power Quality NPTEL course, and this week we'll be discussing some problems on the converters, various type of converters and power factor correction and all those things, right? So before that, my slides are visible to you, right? I can also see that in the screen. So slides are moving and visible, right? And voice is also audible. So any doubt from the previous week assignments before jumping into this topic? If you have some doubt, get it cleared, right? Yes. Any doubt? So if there is no doubt, then I will just jump into the problems on the converters, right? So coming to the first problem, we have a single phase bidirectional boost PFC. So anybody knows what PFC means in DC-DC converters? Must have seen in the lectures also. So you have these DC-DC converters, right? These buck boost and buck boost variants. Actually, all the converters are either like buck boost or buck boost variants. Like many converters you must know, but their functionality actually is to buck boost or buck boost. That is step down or step up the DC voltage levels, right? But here you have this AC DC. Why? First, tell me why you need PFC. What do you mean by PFC? And why you do it?
Power factor correction.
Yes. So why we need power factor correction actually?
Because if power factor is not unity, then losses will be there.
Yes. So whose power factor we are talking about?
Load.
Power factor of?
Load.
No, power factor of supply we are talking about, right? Because see, load
Okay.
will never have unity power factor, right? And loads may be also of DC load nature, right? So there the power factor does not have any implication. If the loads are of DC nature, then you cannot say that it is not unity power factor or something like that, because DC loads will only consume active power, right? Clear?
Yes, sir. Yes, sir.
So then the term power, also AC loads may not be of unity power factor always, because whatever the load has, load structure, whatever how, but the nature of the load will define what its power factor is, the load side power factor, that you cannot control. We cannot go and tell the users to not to use that load. But loads have their own characteristics, their own power factors, their own nature of currents that they will draw. Just like we saw in the previous sessions, that they have their own nature of currents. When you plug in load to they will draw some non-linear or linear whatsoever. That depends on their characteristics, what the components are attached with that load. So load power factor and load currents we can't regulate. Only we can regulate that okay, the load rating is within the rating of the design system. Whatever system we are using, the load should be within that rating. That we can tell. But if you want to regulate the load power factor, you cannot do it directly. So what you can do, you can interface some converter feed the load that much power what it requires, and also make it appear to the supply as if your load is behaving like a unity power factor load. So with some converter, if you use some converter, for example, we are talking about DC loads, for example, or AC loads also, some DC loads or AC loads also. So then we can have one second. Yes, so what I'm telling that we have maybe some DC loads or maybe we have AC loads, doesn't matter. But what we want, these converters will make it appear to the AC supply, because anyways you have these loads connected to the loads maybe of DC nature. For example, here you have some loads or some AC loads maybe connected to this link. But here we have another converter where we have the supply. This is the supply. Or you have some AC to DC converter here, and you have the supply. So this AC to DC can be broken down into two stages, right? First we have to rectify, and then we have to feed the load, or coupled, or some coupled arrangements may be there, like direct AC to DC stage. So number of power stages may vary. But what is the aim? That whether the load be of DC nature or AC nature, we should feed the power to the load from the supply as if it is apparent to the supply that the loads are of unity power factor nature. So that will happen because of proper control of these converters. And you can feed the power to the active power to the load at unity power factor. So unity power factor of supply we are talking. Supply means the AC side here. This is the grid or supply or whatever the AC supply. So that power factor should be unity. Now the question is why the supply power factor should be unity? Can anyone of you tell? Why the supply power should be unity? Anyone?
To provide the active power.
But non-unity power factor also provides active power. So for you have some additional advantages. What are the advantages? That for unity power factor you can feed the amount of active power at the minimum possible current. That is, the amplitude of the current will be minimum for get that given power which you want to feed to the load. If your power factor is unity and you want to feed X watts of power to the load, your current amplitude will be minimum. What will happen for that? The losses will also be minimum for that, for unity power factor operation. Otherwise, what will happen if the RMS value of the current drawn from the supply is more? In case of non-unity power factor, then IRMS square into R feeder or R line, you can tell, that will also be more. So you have more heat and more loss. So who will pay for that loss? The user is not going to pay for that loss, because what you know, how the reactive power looks like. Can anyone tell me? How does the reactive power look like? Just get a real feel about it, how the reactive power looks like and how the active power looks like. So if you have sinusoidal voltages and sinusoidal currents without any phase lag, then you can tell it is unity power factor. So if you multiply the two, it will be like this. So the active power will look like this. But if this is a active power, right? But how the reactive power will look like? See, for example, instantaneous, I am telling, okay? So if you have voltage like this and currents like this, for example, 90-degree shifted, okay? So like this, you have. So if you multiply, you will find it is a sinusoidal waveform. Agreed or not? What is the multiplication of these two? Sin theta, cos theta. If you, for example, like this, then 1 by 2 of sin 2 theta, I can write. So multiplication of sin theta and cos theta is nothing but another sine with double the frequency. So reactive power will look something like this with double the frequency. So it will come and go. That is, it will flow like this and then back to the source. You take something from the source and then return it in the next cycle. This plus positive half cycle you take and then you give. Like you can, this way you can imagine. So reactive power is not consumed anywhere. It is taken from the supply and then given back. This concept is clear? Hello? Yes, I am audible. Hello?
Yes, sir.
Yes, sir. Yes.
Okay, so what I am telling, reactive power is not consumed anywhere. It is taken from the supply and then returned back. Okay. So for that, your users will not pay anything because the meter will not record that. But who has to pay the penalty? The consumer don't have to pay anything. If he is not consuming, then he doesn't have to pay anything. But who will have to suffer the loss due to the dissipated heat and losses at the lines? The generating stations, they will have to pay for that because no one is paying for that much generated power. So that's why actually a limit on the power factor, the usage levels of the consumers are imposed, and a two-part tariff or three-part tariff even is introduced. You must have seen, to penalize the customers for exceeding that is their maximum reactive level of demands. If they exceed those demand levels of the reactive power, then they should be penalized, and they are penalized in the current tariff structure. Okay, so that's why we want PFC for your devices as well, like for EV charging applications and also for some feeding some loads or charging some batteries. For e-rickshaws also, some chargers are there. So for those, you must be taking the power from the grid at unity power factor in a controlled way such that your converters also fulfill the requirement of the load, that is the batteries, and as well as meet the requirement of the meet the guidelines prescribed by the grid operators. Okay, so that's why PFC is seen. And to minimize the power stages, we can embed these two conversion stages from AC to DC and DC to DC into one. That is direct AC to DC. So that is also possible. Otherwise, you will have two stages. One is rectification stage, where you want to convert from AC to DC, and then DC-DC converter like buck boost or buck boost will be attached to that. And then you can feed the load in a controlled manner. So the regulation of the voltage and all those things will be done by the DC-DC converter, and the AC-DC converter will be responsible for the controlling the currents. And you can also make it bidirectional, like here. In some problems, it may be bidirectional. So can anyone say what the bidirectional word refers to and what it is its implication? Yes, hello. So why you need bidirectional? Yes, please feel free to answer. Okay. This session is meant to be interactive, right? So not I will that solve any problem. Otherwise, I can give you the solutions also. So that is not meant for this session. So please feel free to be interactive, right? So why you need bidirectional? That is why the power transfer needs to be bidirectional in these kinds of applications. Can anyone tell me? Or for what type of applications you need bidirectional converters, right? So just I will ask you one question to be more. For example, let me do it here. Let me show you one thing. For example, you have a single phase AC supply, right? And then you have some diode bridge rectifiers. For example, you assume some impedance, source impedance, it is there. And you have some diode bridge rectifier. So what the diode bridge rectifier, and also assume some capacitors, right? So what this diode bridge rectifier and capacitor arrangement will do, it will convert the AC to some DC voltages. Like this is the AC, and here it will be, because of the capacitor, it will be your DC, fully DC, right? Because the ripples will be absorbed by the capacitor. Now you can use your boost converter, whatever the boost converter or buck boost you are connecting. with some switches, as you have learned, and you can feed it to the loads. Loads may be here, okay? So this may be the load. And you can control the voltage across the load. But this is an uncontrolled device. So can anyone tell me whether a diode bridge rectifier is bidirectional or unidirectional? Will it allow power transfer? Which direction will it allow the power transfer? So DBR, this is called diode bridge rectifier for AC to DC transformation. And this device is unidirectional or bidirectional?
Unidirectional.
Power flow. Yes, please answer.
Unidirectional.
Unidirectional, correct. So the AC to D and another question: the DC to DC stage, is it bidirectional or unidirectional?
That is a bidirectional.
Yes, can you please be a little louder? Hello.
Bidirectional.
How you are telling bidirectional? I am talking about power, okay? Unidirectional power flow or bidirectional power flow. By the term unidirectional power flow, I am meaning that it should be able to throw the power from AC to DC side as well as DC to AC side for bidirectional. And for unidirectional, the power will flow only from the AC side to DC side. So then my question will be that okay, agreed. Why did you get the point? Why the diode bridge rectifier is unidirectional? Because for positive half cycle of voltage or either the negative half cycle of voltage, the current transfer, that is the AC current, will only flow from here to here, that is from AC side to DC side. And if you calculate the active power, it is always transferred from AC side to DC side only, this direction, from source to load. So for this device, the total system is becoming a unidirectional power transfer system, where you can only charge the battery, not utilize the battery power, I can say. That is the energy that you stored in the battery for providing support to the supply for some other purposes. So that's why I asked you what is the requirement for such bidirectional power transfer systems. So this is a system, right? This part is a system. This system can be designed as both bidirectional and unidirectional. Can anyone tell me how can I make this system bidirectional? Yeah, no one is answering. Hello? If you don't answer, you will not get this. Yes, please be loud.
Sir, by one diode we have to put in parallel with the system.
Correct. So that is one arrangement you can do. But are the diodes controllable device? Can you control the diodes? No. Can you control their turn off and turn on? Because that is very much necessary for for your power factor correction. Because you have to use some control arrangements. There are various control arrangements, but like you must have seen that in DCM you can do the power factor correction, like peak current mode control, or all those things are there, where you can naturally achieve those unity power factor operation. But for that, control is necessary, switching action is necessary. And the switches also provide another facility, that is to make the power transfer bidirectional, because switches can conduct either in positive half cycle, that is positive direction you can say, or in the reverse direction due to the body diodes, right? So what you can do, you can do some synchronous arrangements. Any one of you are aware of synchronous rectifiers or synchronous operation of two switches? So you can connect a switch here, which will make this DC to DC stage bidirectional. As well as what you can do, you can replace these diodes with switches. Switches means I mean to say MOSFETs or IGBT with some body diodes. Because MOSFETs naturally has a body diode with them, so you can conduct either ways. Either you can take the power from load to source or can take the power from source to load. That is one arrangement. Or you can connect some IGBTs with some body diodes. Body diode is necessary such that, or anti-parallel diode is necessary such that you can conduct the current or the power in both the ways. So that's how we can make the devices or the systems bidirectional, along with achieving the power factor correction. So both are both can be done. You can do power factor correction for unidirectional as well as for bidirectional. But for bidirectional, additional advantage is that your device is more controllable and you can utilize the power stored in the battery, or the loads can have regenerative action, right? So that it can support the, I can say, supply. By supporting the supply, can anyone tell me what are these applications for bidirectional? Because this is interesting, right? So what applications you need bidirectional power transfer? That's what I was asking. So what applications? Yes, please answer. For what applications you need bidirectional power transfer?
Electric vehicle.
Correct. Because you want some regenerative action also, right? And apart from electric vehicle, why electric vehicle? Because the electric vehicle is sitting
For
here, right?
charging purpose.
Yes, correct. Charging purpose agreed, but what he told, electric vehicle, the load is the electric, that is the battery. The source is the battery. For the electric vehicle, a DC-DC stage kind of stage, I can assume that the battery motors are there, that the EV wheels are there, which are acting as the load for which you have to power the motors, and from motors you can charge the battery. That's what you are meaning to say.
Yes, sir.
Yes, for that you need just simple DC-DC converter will work, right? Or AC-DC also you can do. So both are possible. So that there no supply is there. Actually, supply becomes DC. Okay. So reverse scenario is there. So supply is DC because you have the battery, and you are running some synchronous motors or IPMSM such that your whenever regenerative, you can use regenerative action to slow down the vehicle. Whatever he told, to utilize the energy of the wheels to charge the battery, because your aim is to slow down the vehicle, so not to dissipate the stored kinetic energy in the wheels, and just dissipate it in the environment using mechanical brake pads. Otherwise, you can use also the energy stored in the wheels to charge the battery. That's why bidirectional power transfer he meant to say. So that is one application. But why in AC to, that is supply? What I meant to say, if the supply is AC, that is the grid, and you are feeding some charging loads, some electric vehicles, some rickshaws, e-rickshaws also. So why is regenerative action very useful? Sorry, not regenerative, bidirectional power transfer, because the vehicle is just standing there. And in that case also bidirectional power transfer is very much useful. Why, can you, any one of you tell? So have you heard of terms like V2V and G2V, B2G? These terms, have you, any one of you read somewhere in some papers or some, or heard of these terms? V2G, V2V. Any one of you? Have you heard of these terms?
Sir, vehicle to vehicle, vehicle to grid.
Why vehicle to grid is very much important? Because there the power transfer is opposite, right? From grid to vehicle in normal condition, power transfer is happening to charge the vehicle, as your objective is to charge the vehicle from the grid. But I can also tell V2G mode exists. Why it is useful? V2G mode is the reverse of G2V. So why that is important? There the power transfer is bidirectional. So that mode is important because not always you need to charge the vehicle at the, not in all condition. For example, you have 10 hours in your hand. I am giving an example. You don't want that your vehicle should always charge in that 10 hours, because for your vehicle to charge maybe 30 minutes, maybe useful. Or in 30 minutes you can charge your vehicle. But in night, you are connecting your vehicle at your home. I can tell you are connecting the vehicle to the port, and you are leaving it. So what you can do, you can utilize the battery in the vehicle to provide support to the grid, to minimize also the tariff that you actually incur, because sometimes your tariff rates are fluctuating. So you can sell the, if you can use the battery, EV battery, to provide some support during those increased tariff periods, then you can save some money, and again start charging the battery during the low tariff rates. So there your battery was useful. You utilized its stored energy that you stored within it at the cheap tariff time, to provide support during high tariff time. So there the battery is very useful, because you have more time in your hand, and you can play with the battery. You can use the battery for other purposes also to provide support. So that's why the B2G mode is becoming very popular. And in a kind of a shared environment where you have more vehicles, you can use those also to support the higher charge batteries. You can EVs, you can use those higher charge EVs to provide support to the other neighboring EVs who are having lesser charge, or provide support to the grid. So this mode is useful, and that's why bidirectional power transfer is very useful for these kind of applications. So that's the meaning, that you need some converters with some switches, like IGBT based switches, some voltage source converters, whatever we were talking about in the course, that you need. And the problem begins from there. So once you understand that, the problem you can solve. So you have a single phase supply, whatever I told you, and you have a AC to DC arrangement, as you understand, because you have a boost PFC. So boost converter. So whenever you read this, you need to understand that the boost PFC means that your load is of DC type, where you want to feed DC loads, and you have supply as AC. So you need to use a AC supply, then you have to use a converter, then you need to connect your boost converter, which is a DC to DC converter, and after that you can connect the load. So load here is a resistive load, and supply is 230 volts, 50 hertz, normal single phase supply, and the power drawn is 1500 watts, whatever is given in the problem. So the converter switching frequency is also given for you, which is 40 kilohertz, and the source inductive reactance, because in AC systems you must have read the X by R ratio is higher. So R you can neglect and just replace by X, which is a inductance. So model it as a inductance, the source impedance, as 1 ohm. So reactance is 1 ohm. And then you, after knowing this information, you are asked to calculate the value of the fundamental component of PWM voltage. So PWM voltage, where it will appear? Can any one of you tell me? So this side, if you can see the diagram in the slide, in the first diagram, this side your voltage is purely sinusoidal, right? So where will the PWM voltage of the converter appear? Because this side is DC, and I can draw a capacitor here, and inside this your whole arrangement is sitting. So this is VSC plus boost arrangement, just like I draw here. This is the voltage source converter, where you have switches, some switches, bidirectional switches, and you have also some synchronous arrangement here. So this total system I am describing here as AC/DC. So AC to DC stage by the converter, and DC to DC stage by the boost. So please remember this. So if you have this, can any one of you tell me where the PWM voltage will appear for this kind of converters? Where the PWM is voltage? PWM voltage means the square pulse voltage, because these are two level arrangement that we are doing. So PWM voltages will appear, and the average of the PWM voltage within a switching cycle will give you 1 point of the sine. Over a 50 hertz, you will see the sinusoidal wave. But whatever it is actually creating in a switching cycle is a 1 PWM pulse voltage, you can tell. So that, knowing that, where will the pulse voltage appear? On this side or this side? A or B? Can any one of you tell me? The PWM voltage will have switching harmonics also within it, and other harmonics also. Depending on the size of the inductor and selected rating of the inductor, you can eliminate some harmonics such that you can connect these two. That is a different thing. That's why you use interfacing in inductors in converters, but can you tell me which side the PWM voltage will appear? Hello?
The AC side.
AC side. That means for this point, right? B. The PWM voltage will appear here, right? Because here you are tied to the grid. Grid does not have any harmonics or such like that. The converter will have harmonics, PWM ripples, all switching ripples you can take. Switching harmonics in the voltages, in the AC voltages. You need to filter out using the inductor. The source impedance is enough to filter out those switching harmonics. Otherwise, you can also create some filter arrangements. Also, we are providing capacitors, right? So those will also mitigate some portion of the ripples. So using those filters and inductors that where you are utilizing the source impedance only as the filter, you are mitigating the PWM voltages. So now what is asked? So this inductor is allowing the power transfer between the supply, that is this A to point B. That's why the power transfer is happening, right? So what is asked is the value of the fundamental component of PWM voltage. So can any one of you tell me if you recall the power transfer happens for, I told you, fundamental component only, because you are doing PFC. Assuming that your converters are operated at PFC to achieve PFC operation, such that in that way only you are controlling. If you assume that PFC operation is attained and your converters are controlled in that way, then you can tell that power transfer is happening at, that is your supply is throwing purely active power, right? Agreed or not? Because if you are achieving UPF and your V and I are both sinusoidal, then what is the meaning of unity power factor? Your voltage and current both are purely sinusoidal, and they don't have any phase shift between them. If those are the two conditions, then you can tell that the supply is throwing purely active power to the load. So knowing that your supply is throwing purely active power to the load, you can tell that power transfer happens only because of the active component, because otherwise your voltage and current components don't have any harmonics within them. So also we can identify one thing, that first of all, the power transfer is happening at unity power factor. Second, so I will write, so maybe I can just erase this portion. After you understand the concept, it is easy, right? So this is the scenario, right? The power transfer will also happen purely active power will be transferred. If you draw the instantaneous power, then it will be like this, right? So P inst I can tell with time. So remember, power transfer happens only due to same frequencies of voltage and current. And if I write active power transfer, then active power transfer will only happen due to same frequencies of voltage and current, as well as they should have no phase mismatch, right? So active power transfer happens only due to same frequency of V and in phase component of I, because that is the definition of active power, V and in phase component of I, because it should not have any shift. So knowing these 2 points, now you tell me, can you calculate the amount of active power transfer between these 2 points? Because the PWM voltage is happening at point B, PWM voltage from the VSC, and point A is tied to the grid. Now, if I write the active power transfer equation, then that active power transfer should be happening for the fundamental component of the PWM voltage. So there is fundamental component, right? So can anyone tell me what is the expression of power transfer between points A and B? Point A voltage I know, point B voltage I need to identify, that is being asked in the question. Now point B voltage fundamental is reason for active power transfer. And also I know the inductive reactance. Can anyone just spot? And the phase shift is given, right? 1.6 degree. Can anyone spot? the power transfer expression. You must have learned synchronous machine and power systems. So there you must have seen the power transfer expression between two nodes where you have inductive reactance in between them. So what is the expression? What I can write? P. Please tell me. What I can write P as? I know this point voltage, this point voltage. For example, I know VA and VB by XS sine delta. Can I write? Where V and V, VA and VB are the voltages at those two nodes, the amplitude of the voltage at those two nodes. So I can write mod VA, mod VB, and delta is the phase shift between those 2 points. The phase shift between the voltages at those two nodes. So can any one of you tell me that power flow happens from which point to which point? Point A to point B or point B to point A? If I know that the delta of this node, for example, VA and VB, we have two voltages. If I tell you that delta, this VA is 1.6 and this VB is 0 degree, can you tell me where the power transfer will happen? From which point to which point? Power flow happens from which direction to which direction? How can you identify? By delta. Always you should know that power transfer happens from higher delta to lower delta. That is the rule. Why you can see in power systems, those books, they are explaining well that why the active power transfer should happen between higher delta to lower delta. So always the power transfer is linked to the delta, the voltage phase angle. So the one bus or one, we can write node, which is having the higher delta or higher phase voltage angle, will transfer the active power to the lower bus voltage angle, which is lagging compared to that voltage. So which one of these 2 points has higher delta or lower delta? Because if this is bidirectional, we can generate higher delta or lower delta voltages at point B, because point B voltage is in our control. So I will ask you one question. If I want the power transfer to happen from point B to point A, what shall my converter have to generate? Delta higher than point voltage at point A or lower than voltage at point A? If I want my power transfer to be happening in this direction, B to A, then what should be the delta angle of the voltage at fundamental of the voltage, obviously, at point B? Higher than A or lower than? Any one of you? Because these may be asked in the exams, right, as MCQs.
Higher than point A.
Yes, higher than point A. And your control is with the VB. Similarly, if your power transfer is happening from A to B, then obviously because your control handle is the VB, so that voltage phase angle, that should be lower than point A. I hope you understand. So now, given a scenario that your delta D or whatever you tell, the phase angle difference is 1.6 degree, can you find what is the, because you need VB and VB is the fundamental, because active power transfer happens for the fundamental. Now, what we require? You require VB. VA you know 230. Please find what is the value of VB. Answer is one line, but concept you need to understand, right? So VB is PXS by VA sine delta. Please find what is the value of VB. You calculate. XS is 1 ohm. Power is 1500 watts given in the question, and VA is 230 volt, and VB is nothing but fundamental of the PWM voltage. Sine delta you take sine 1.6 degree. So what it is coming? Calculate. Hello. What is coming? Please, any one of you calculate. You should do with me, right? Please do this question. First one you should do, right? Please find the answer.
So what is delta? Delta value?
Delta is the angle, difference angle between point A and point B voltage. This is given as 1.6 degree. Phase shift, right?
Okay.
Delta is a denotion. You can replace by theta also, but in generally power systems we define by delta. That's why I wrote delta. So since you don't have any harmonics or analysis involved in this question became easy. This question can be made further complicated using some harmonic currents, right? So that is not done here. And also in the exam also you will get easy questions. So our purpose is to make you learn, but this question would have been, analysis would have been much more complicated if the current would have some harmonics.
So 233.5.
Correct. So this is the answer, 233.5. I hope the slides are lagging. Yes, now it is visible. 2 volts. So this way you can solve the questions, right? PFC questions. You assume that it is unity power factor, and why you are able to do that? Because it is unity power factor. If it was not unity power factor, then you had to determine the active power transfer. That is the active power transfer magnitude, right? What is the active power being transferred? After that only you can do this, apply this formula. But you are doing PFC here, so no need to worry. You are already assuming it to be a unity power factor system from the supply side. That is the thing. So I hope the slides are lagging. Just let me refresh. My screen is visible or not? Screen is not visible, right? Yes, now it is clear. So now for the previous problem, can any one of you determine the modulation index? That is what is asked. So any one of you know modulation index? What is the definition of modulation index for a converter? Yes, I want some answers. Hello. So if you just see from the AC side to DC side, right? For an inverter also. Yes, my voice is visible, right? Hello. Hello. Voice is visible, right?
Yes, sir. Yes, sir.
Yes. So what is the definition of modulation index? I want to hear from you. Because if you don't, if you just can interact, you will remember it more easily. If I tell you, it will be one directional, right? I want the session to be interactive, and every one of you please feel free to discuss, right? By discussion you will gain more insights, and I want more questions. Now no question is coming from your end, so please feel free to answer, and please feel free to ask your doubts, because this session is meant to be interactive, right? So what is the definition of modulation index? Yes, any answer? If you are able to answer this, then you can solve the problem in one line, right?
So it is the ratio of output to input voltage. Like in case
Yes. That's what the output to input voltage. That is the maximum, because output and input voltages are AC voltage. If output voltage is a DC, and yes. Please tell. Hello. Because this is the inverter, right? So here you have some DC voltages with you, and here you have some AC voltages. Now tell what you are telling. If I say the M is the modulation index, what I mean, if this voltage is VDC and this is VAC, the RMS voltage, let's assume a single phase scenario for the time. Then if you remember of the voltage, the line to line voltage in inverter, what is the peak AC voltage of the links? That is the switch node voltage. If you take the switch node voltage only, right? For the AC, switch node voltage means I am telling this. If you have some switches, in this voltage you tap and another this link voltage you tap, right? And then you have some DC link, the voltage available. So these two voltages are what you tap to form the AC voltage, right? So this two voltage will form the line voltage. So what is the maximum amplitude of the voltage? This is √2 times VAC, because this is the peak voltage, peak line voltage available with you. Now in single phase, line and phase don't have any meaning, but in three phase you will get the line voltage, okay, between these two links, because this is for A, this is for B. If I tell, then there is a line voltage. So √2 times V line to line is the peak AC side voltage. And if you see from DC to AC side, from DC to AC, so I will write DC to AC, you get what? Boost action or buck action for an inverter. See from DC to AC, right? So if you provide some DC voltages, you get some AC voltages out of it. So what is that action? Inverter is nothing but a buck converter. If you see closely, inverter is nothing but a buck converter operating at line frequency, which is 50 Hertz. But it is providing a bucking action, because if you increase the DC link voltage, for example, you give more DC link voltage than the necessary DC link voltage, which is the minimum required DC link voltage. What is the minimum required DC link voltage? Nothing but √2 V line to line, because that is the amount of amplitude of the maximum amplitude of the voltage that will be formed at the AC side by switching, two level switching, plus plus VDC 0 and then minus VDC. So what is the peak amplitude of the AC voltage? √2 V line to line. If you keep same as DC link, then also it will be okay, sufficient. Some drop may be there, but sufficiently large to maintain that √2 V line to line. So what I'm telling, if you increase the DC link voltage more than √2 V line to line, then also is it possible to form √2 V line to line voltage? Answer is yes. Agreed or not? Because the switches will be remaining on and off for lesser time, off for more time, or on for less time. If your switch remains on for more time, then your amplitude of voltage will rise. Average amplitude of voltage I'm talking about, okay? Average amplitude of voltage will be more. Your switches remain on for more time. Because V average, 1 second. So anyone having any doubt over this point? Please let me know. If you can not understand this, I will re-explain this concept. So the DC link concept is very important. So if your DC link voltage is maintained above the minimum required threshold also, then also you can form some lower levels of AC amplitude voltage, √2 V line to line, like this example. But can any one of you tell me, what if I maintain a DC link voltage lower than √2 V line to line? Will the inverter be able to form an AC voltage of amplitude √2 V line to line, or whatever is the peak amplitude of the AC voltage? If I maintain a DC link voltage lower than that, will my event be switching for a more longer duration? Then can you maintain that voltage? Please answer from common sense. If you are applying DC link voltage lower than the required amplitude of the AC voltage being formed at the AC side, then by any kind of switching, can you attain more voltages? That is a peak voltage more than that of the DC link. Peak voltage of AC side more than that of the DC link voltage, available DC link voltage. Is that possible by any kind of switching? For sine I am telling.
Yes, sir.
Yes, it is not possible. So it will be a over modulation kind of scenario where your voltages will not be sinusoidal first of all, and the fundamental RMS voltage amplitude that you will see will be lower than your required available voltage. That is whatever you require. That from that it will be low because your DC link voltage is not sufficient to form that amplitude of AC voltage. I can tell. So in order to form √2 V line to line amplitude of AC voltage, your DC link voltage should also be minimum √2 V line to line or more than that or higher than that. So higher DC link voltage means from DC to AC side you are having a bucking action by switching. If you also see the switch, it is a buck. It is a buck converter, right? So one switch, one diode. When one is on, another will be off, and it is a buck converter only because this side you are getting this one. If I say another is neutral, so this side you are getting the AC voltage. This side you are giving the DC voltage. It is nothing but a buck converter, right? With some inductor is there, the source impedance is there. This simply resembles a buck converter into action. So that's how. So the definite from that idea only, that inverter is giving a bucking action seen from the DC to AC side, the concept of modulation index or whatever is the amplitude reduction, amplitude bucking I can tell. Because in DC-DC converter, what term you use? So in AC-DC converter, something should be there. So that's why M. These two has correlation. And naturally, if you see from a DC perspective or low power line frequency perspective, those two are congruent, right? These two can be simply seen like complementing each other. Like for AC to DC, we use N, and for DC to DC, we use D. Same action. So whatever is the level reduction, we can tell like that. So this is a fraction, right? Modulation index is a fraction. So obviously VDC will be lower because these are less than 1, and VAC peak. So this is M. So now can you give me the answer of this question? What is the DC link voltage? Anywhere it is written VDC, right? Just see. Previous problem, DC link voltage should be given, right? So what is the value of M? Yes, any one of them. So this is, I can tell. What is VAC peak? Can anyone tell me? Fundamental. Okay, remember fundamental. So if I write somewhere here, just do with me, okay? If you get the answer, just tell me. Let me do with another color. So what is M? √2 times V, I can tell B1 because that we found out in the previous thing. So √2 times that peak amplitude I am telling. Previously we found out the RMS value and divided by VDC. So just assume for this problem DC link voltage as 380 volts because that is given actually. Okay. So now can you find out what is the value of M? Just plug in the previous values. Previously what you got, RMS value of fundamental PWM voltage, that you plug it in here. What is the answer you got? 233.5, right? and divided by 380. So what is the answer coming? M. From definition of this index, just tell me the answer. What is the operating? You can tell this modulation index is just the operating point of that converter. It will give you that idea. Just like the DC-DC converter, you have duty ratio, that like that.
0.08.
So 0.08. Okay. 0.08. Just recheck.
0.87.
0.8, right? Yes, yes. Then it is correct. Just let me confirm once again. 0.83 I am getting. 0.8. Okay. 223, 233. Okay, okay. 233 it was. No? Yes, 0.87. Correct. So this is the answer, right? Simple. You go ahead with the definition and then you'll get it. So let us see the next problem, right? So read the problem. So a bidirectional boost PFC, again, you have a bidirectional boost PFC and it is single phase, right? AC to DC bridge one is bridge converter and another is bridgeless. So bridgeless topologies are also there in PFC, where you have just one stage and you eliminate the bridge. That is also possible. You can see that. So 2000 watt is the power. Power can flow in either direction. And you have connected it to a 230 volt 50 hertz mains, just like the previous problem. And 20 kilohertz is the switching frequency of the converter. And the AC inductor of the, obviously the source inductor impedance, 2.5 millihenry. And power factor correction is there. And maximum PWM modulation index is 1 to operate in the linear range. And because above that you will go to the non-linear range, right? Because over modulation or under modulation, you must have heard these terms. So we want to maintain it in the linear range where your M is between 0 and 1. So the converter is controlled so that AC mains current in either in phase or out of phase from AC mains voltage. Okay, so what he means by that? What is this line means? Can anyone of you tell? Either in phase or out of phase? Both ways you get unity power factor or not. If your voltage is like this and your current is like this, overlapping, no phase difference, or your current is like this. So 0 degree phase shift, V and I1 I can tell, and I2, 180 degree phase shift. So both ways cos 0 and cos 180 will be 1, right? Power factor will be 1, right? There is no concept of -1, right? Cos 180 degrees -1, but we don't tell like that. We tell it is unity power factor operation only. So agreed or not? It is -1, cos 180 degrees -1, but we don't tell like that, okay? We tell the power factor is unity. So that's it. That's what it is telling. So now determine the RMS value of the fundamental component of AC mains current. So that is what it is asked. Now you see that you have a boost PFC and you are being asked. Previously you were asked the RMS value of the fundamental component of the PWM voltage. Now you are being asked the current that is pushed from the supply side towards the load for a bidirectional boost PFC type of topology. So again, can we apply that power transfer concept? Yes, we can apply. But here we also need the value of the current, because here your voltage is not asked, the fundamental component of the current is asked, assuming that it is a unity power factor condition, right? So how will you determine? Anyone? Yes, hello. Anyone? Hello. I want the value of the current, RMS value of the current. Is it that difficult? So assume a lossless, obviously assume lossless scenario. because whenever these problems are given to you, you don't have to assume the effect of parasitics. So you can assume the power thrown by the supply towards the load is actually the power that is being absorbed in the load. So obviously assume lossless scenario. So P in you can equate it to P out, or I can tell PAC equal to PDC. So what is the value of PDC? Anyone? What is the value of the PDC? That is the DC power or power transferred. What is the value? Given in the question as 2000 watts. So PAC I can assume that is the AC power that is being drawn from the supply is 2000 watts, right? Now I also know that the power factor is unity and the RMS value of the voltage I know. Then I can find the RMS value of the current. So cos theta is 1. So what is IRMS? Fundamental, because power transfer always happens for, I will write once again. Power transfer always happens for fundamental, right? Fundamental of V and I of same frequency. Now you have, for this problem you have only one frequency of voltage. So for one frequency of current only the power transfer will happen. Now if the voltage also had third harmonics, then the third harmonics current would have also contributed for your power transfer. But here you have a UPF scenario. So the voltage is sinusoidal, current should be sinusoidal. And there should not be any phase shift between them because power factor is unity, right? So IRMS1 inherently will come, for which the active power transfer will only happen. So IRMS1 is P by V into what? Cos theta is 1. So P by V RMS. What is P by V RMS? 2000 by 230, right?
8.69.
Correct. 8.69 amps. So this is only the fundamental RMS value. So remember this is RMS value, right? This is the phase voltage or line voltage, whatever you tell, single phase it is, so line and phase all are same. And this is I can say RMS current, not peak. So someone was confused. So always when you calculate the power, you get the RMS values of the currents. So if it is star connected, then you would have to apply accordingly, that whether 3 V phase into I phase you will do for phase quantities or √3 VL into IL. So for 3 phase, right? But this is a single phase. So V into I into cos phi. Now cos phi is 1. So P is nothing but V RMS into I RMS. For your convenience, I am writing into cos theta. I RMS 1 I will write. So cos theta is 1. So P by V RMS 1, which is nothing but V RMS, is nothing but 230 volts. So P by 230 volt is 2000 by 230. It is nothing but 8.69. So this is the answer, right? So next problem we are moving. So likewise, now we move on to the more intricate details of the converter, that maybe you have just studied the boost converter. Otherwise, I will just draw how the boost converter looks like. So this is nothing but you have an inductor, you have a switch, and then you have some diodes. So this is the, I can tell, VDC in, and this is the VDC out, right? And obviously this side you have the converter VSC, which is forming the DC voltage from the AC side, and this side you have the load. Before the VSC you also have the supply, AC supply. So likewise, and you have the capacitors both sides for ripple reduction. Now what is the problem telling? Single switch boost PFC. So can anyone tell me what is a single switch boost PFC? This part is the boost. What is a single switch boost PFC? Just I discussed some slides before.
Unidirectional.
Correct. So by whatever you meant, actually that one switch and one diode. So for one diode you cannot have bidirectional, right? So it is written in a different language. So don't be confused. Just understand in the exam that single switch means it is unidirectional only. So boost PFC AC-DC converter. Obviously it is AC-DC because the supply is AC and the load is DC. So you need two power stages, or bridgeless scenario also exists. But for this case you have a AC-DC converter, and with the following specifications of 800 watts and your output voltage. So again assume lossless scenario. Okay, P load is 800 watts given in the question, and your output DC voltage V out DC is 400 volts. So the boost converter output is 400 volts. You need to understand, and the boost inductor value is given, right? Not the source impedance inductor. We are talking about the boost inductor. This 3 millihenry. This inductor, as you can see in the slide. Supply AC voltage as usual 220 volts 50 hertz, and the switching frequency is 20 kilohertz. Obviously for these two both. So for CCM operation we are talking continuous current conduction mode of the inductor currents. Now calculate the percentage current ripple in the boost inductor corresponding to peak supply current. So it is asking you to calculate the maximum ripples in the boost inductor. So how will you find? So ripple in inductor current is the question. Now during switch on, you know that the boost inductor will charge and then it will discharge. In every switching cycle will happen like this. So likewise, you are asked to calculate this portion, this delta IL. This is the delta IL. That the ripple in the inductor current. Peak to peak ripple, okay? So what is the approach? You must have learned boost converter and how to calculate that ripple. So see, this is duty times TS, T on, right? What is the definition of duty? This is T on by T on plus T off. So this is T on plus T off means TS switching 1 by TS is switching frequency. So Fs equal to 1 by TS, and DTS is nothing but T on, following from this equation, right? And also to get the relation of TS with Fs. Fs is given 20 kilohertz. So for one particular instance of switch on or switch off, you can apply the inductor ripple equation where you have L di dt is equal to V. So whatever is the voltage impressed across the inductor during one instance, whether it be switch on state or switch off state, you can calculate the value of the ripple, because either way the ripple during switch on state and switch on off state and switch on state are both equal, because you are having a continuous current conduction mode. Continuous current conduction mode means that wherever you started from, you get back to that point after a TS, 1 TS. So you should have that, you should be returning to that point, follows that you should have same amount of ripple during switch on and switch off. So delta, so L into delta IL I can write, because this is the amount of ripple, and time is D times TS. During switch on I am doing. So what is the applied voltage across the inductor during switch on? Can any one of you tell me when this switch is on? What is the VL, inductor voltage? Voltage applied across the inductor, what is that? Yes, it is easy, right? Please be interactive. What is the voltage applied across the inductor when you switch on, turn the switch on?
DC link voltage.
Yes, correct. DC link voltage. So what is this DC link voltage input? Are we given that? Or else we can also do with the switch off state, right? But we can write this. So this inductor value is nothing but V in into duty divided by Fs into delta IL, because this follows from this. This is agreed, right? This is given, right? 400 volt is the output DC voltage. And this is the output DC voltage, and input DC voltage we need to determine. So what is the input DC voltage? Can any one of you calculate? Because modulation index I need, right? Modulation index it is given. Yes, how will I calculate this DC link voltage? Yes, I want to hear. Any idea? So 220 volt is the RMS voltage, and you have a unidirectional PFC. So what is the value of the DC link voltage? This is easy, right? What is the meaning of unidirectional boost PFC? What is connected between the supply and what you are using? Yes.
Root 2 into 220.
Correct. So that means you are using a diode bridge rectifier, right? DBR, to convert the supply, because this is not actually a VSC. This is a DBR sitting here. Because you have unidirectional power supply, so you don't need a VSC for bidirectional power transfer. You need only a DBR to convert the supply voltage to DC link voltage, to DC voltage, to the input of the boost. So knowing that you are using a DBR, what is the value of the DC link voltage? 2 root 2 Vm by pi, I already told you, for single phase. So what is the value? Calculate. 2 root 2 by pi means 0.9 into Vm RMS. Is Vm RMS 220 volts. Okay, what is the value? Calculate. Yes, hello. So please calculate the value.
198.
Correct. 0.07 volts, right? So now you know VDC in, the input voltage, input DC voltage to the boost. Now also you know the output boost voltage, DC voltage, 400 volts. So either ways, you can find delta IL. But for that you also need duty. The duty value also you need, right? Because V in I know, V in DC, Fs I know, delta IL I need to find, L I know, duty I don't know, but I can calculate that for a boost converter for ideal scenario, it is 1 minus V in by V out, right? Or you can write 1 by 1 minus D is V in by V out, right? Or V out by V in, sorry. Correct? So what is duty? Duty is 1 minus V in by V out. You can calculate V naught minus D V naught equal to V in. So V naught you take common, or V naught minus V in by V naught is D V naught, is D. Then 1 minus V in by V out. Yes, this is correct. So can you find duty value? What is duty value? V in V out you know. Just tell me 1 minus V in by V out. V out is 400 and V in is 198. 198 divided 400, 0.5, around 0.5, right? So you plug in values and tell me what is delta IL. From this equation you tell me. Delta IL is LFS divided by dV, right? What? Sorry, delta IL is, yes, dV in divided by LFS, right? So you tell me this value. What is value of delta IL? dV in divided by LFS. Calculate L value you know, switching frequency value you know, 20 kilohertz, and T is 0.5 and V in is 198. So you'll write V in as 198, Fs as 20 kilohertz, and your V in and Fs I wrote. So now I will write L value is 3 millihenries, and what else? Duty is 0.5. So using this, calculate delta IL. What is the answer coming? 0.5 into 220, sorry, not 220, 198 divided by L into Fs. L into Fs, right? L into Fs. So 10 to the power minus 3, and that will cancel. So what is coming answer?
1.60 ampere.
Yes, around 1.6 it is coming, right? Correct? 1.6, right?
Yes, sir.
Hello? Yes, so calculate percentage current ripple. What is percentage current ripple? To know the percentage current ripple, you need to know the average inductor current. What is average inductor current? Can anyone tell me? For a boost, it is nothing but the supply input current. IL average is nothing but the input current average, which is responsible for the active power transfer, because this inductor is carrying the input current. And its DC part should match with the active power transferred, right? So what is the active power transferred? It is 800 watts divided by 198. So calculate what is IL average.
4.04.
30%.
4.04 IL average, right? So now calculate percentage IL, percentage ripple. You divide your 1.65 with 4.04 into 100%, right? So what is this coming? 1.65 divided by 4.04. So around how much?
Thirty percent.
40.84.
But it is asking for peak supply current, right? Have you seen that? That line you should see. What we are calculating is the RMS value, right? Hello? Hello? Is any confusion here? These currents all will be in power frequency, right? Will be sinusoidal only. Only the DC part will be there, that top part, right? Because your input signal is like this, but you are not using any capacitor after that, directly connecting to the boost, then what will happen? Your currents will be like this in power frequency. So for the peak amplitude current, it will be root 2 times, right? The average value. So did you get the concept, or I should repeat? That your power transfer is happening for these sinusoidal currents and voltages, and you are using a diode bridge rectifier. So DC current will also be sinusoidal, but DC side I can tell current will also be a power frequency current, right? For each point you are taking that boost action to give the voltage. Output you are using capacitor, no issue. But input you are applying those voltages. So what is happening? The obviously the capacitor is such value that it will absorb the ripples. But for if you want to calculate the inductor current corresponding to the peak supply current, then peak supply current average value from power we calculated, its value should be equal to what? We calculated that 4.04. That is the RMS current, because current is not purely DC in the boost input. So corresponding to the peak of that means that root 2 times that. So now calculate for root 2 into 4.04. What is the fluctuation? This point, if it is not clear, you can ask. I can repeat. Root 2 times 4.04. So what is coming? What is the answer coming?
5.7.
20 volts, right? 5.14, yes. This is 5.14 root 2 times 4, whatever your that peak. I am wanting that peak AC amplitude, right? That is 5.14. So 1.65 divide 5.14, around 32% is coming. So this is the peak value of supply current they are asking, right? So 1 second, huh? So what was your peak value of inductor ripple current? Delta IL. Just let me write in a different color, okay? And rub a portion. Where can I rub? Maybe some space I can create here. So IS RMS is what? Can anyone tell me? Supply RMS power divided by voltage RMS. So IS peak is that they are telling it to take in the denominator, right? What is IS peak? 800 by 220 into root 2. With that you need to take, because in the question supply current was mentioned, right? Supply means AC supply. So what is that? 800 divide 220 into root 2. So that is 5.14, right? And your delta IL is given as 1.65. Now, since they're asking to take with the supply peak RMS, please read this line. Peak supply RMS, peak supply current. So what is the value? Percentage with respect to percentage IL WRT. I can write IS peak. If you take with respect to that, then 1.65 by 5.14 into 100%. What is coming? 1. If they ask with the input current peak, whatever we calculated, then that will also be a different problem. But in this problem, they are wanting you to calculate with respect to the supply current peak. If they are telling to calculate with respect to the input current peak, then that would have been different. Okay, answer would have been different. So those two are different. There is 32%, right? 32.1%. Okay, I hope this is clear. Any doubt in this problem? Yes, any doubt? Hello? If you have some doubt, please ask. Hello? Can I move to the next problem?
Yes, sir.
Okay. Then see this problem. Okay. This is an easy problem. So all the topologies of the boost till now we did was non-isolated, right? We did not do any isolated topology. Just for your clarity. So this problem is also from non-isolated, right? Isolated means that inductor was there. There should have been a transformer where you are doing the volt ampere balance. So that would have isolated the two sides of the DC. The high frequency transformer is used in isolated topologies. Wherever you need isolation, you can use those topologies. So This problem is easy, I think. So single phase power factor corrected buck AC/DC converter, non-isolated only, simple buck topology, operating at 20 kilohertz with the following specifications. So the voltage and powers are all given, output voltage and power. So similarly assume lossless condition. Don't assume that the bucking stage is having some power loss. All those things you don't need to assume for these kind of problems. So there is an assumption. This will not be given. This is just an assumption and you need to follow, because otherwise you cannot do the computation, right? And 2% DC voltage ripple at the output of the buck is given. So knowing that, you are asked to calculate the output capacitor value. So for buck, I think it is easy. So for buck, this problem boils down to simple finding the output capacitor value of a buck. For buck, you need to find C output or whatever CDC in millifarads. So if you just see the parameters which are given is output voltage 120 volt with 2% ripple, and P naught is given as 300 watts. So these two informations and these three information I can tell are given, and V supply is given to be 220, but you don't need that. You are already know the delta V naught. Can you calculate what is delta V naught? What is the amplitude of the peak to peak voltage ripple? 2% of 120 volts, which is the output voltage. So what is that? 0.02 into 120, right? So 2.4 volts, right? So this V naught, delta V naught. So now CDC is given by P naught by V naught, which is nothing but I naught divided by 4 pi F delta V naught. Okay, Fs, switching frequency. So using that you can calculate the capacitor value for the boost. You can calculate, right? So take that line frequency, okay? Sorry. So which capacitor are we asked? One second, let me see the value of the output capacitor. Okay. Yeah, so you take the Fs, okay? Fs means the line frequency, which is 50 hertz. Fs you take as 50 hertz. Just calculate. So this expression is actually derived in the power quality book. You can see. And this non-isolated single switch AC/DC converter, which is operating at 20 kilohertz. So that DC link capacitance value is actually asked, right? So that for that you can see this is the expression of the output capacitor. So this is nothing but your converter. You are having an inverter, right? This is one, and this single phase, so 4 switches will be there. So with body diode arrangements for. Also you can have diodes, no issue. But you are having some DC link capacitors, right? So this is the AC and this is the DC. So this capacitor is what it is being asked. So this is the CDC, DC link capacitor. Because single switch AC/DC converter, when they tell, this side is the AC, right? This is AC, this is DC. So inherently this is providing a bucking action. You don't need another DC to DC bucking stage. That's why this capacitor is sufficient to provide the load voltage. Because anyways, as I told you, from DC to AC it is From DC to AC side, it is bucking action only. Because DC is higher voltage, AC is lower voltage. So anyways, you don't need another buck for that. Buck stage towards the AC side for 3FC. So this converter is sufficient to be actually behave as a buck and provide power to the load. So for that, CDC is derived in the power quality book actually. It is simple. It is just balancing the that is the power, that is the energy stored and energy released in one cycle. So you can do the charge balance and then get the value of the capacitor, right? So for that, just remember that Fs should be the line frequency, at 50 Hertz, right? So that is the thing. That this is connected here. Okay. So just derive what is the value of CDC. Yes, please calculate. Hello. You can just plug in the values, right, and then calculate. Just let me know the value.
$901.
No, you need to find the capacitor value, right? What is coming? Capacitance value. In farads or millifarads, you tell me.
1.65 millifarad.
1.66 millifarad. Right. Yeah, so this is, I think, the problems. You can just see buck, boost, and buck PFC, boost PFC, and buck boost PFC, right? So for that, you can just see. And you can also have a bucking stage also here, right? So either ways, you can either use buck or the capacitor value can be increased to provide, because inverter just this, if you see from DC to AC, it is providing a bucking action already. So if you need another stage of buck, you can use that also to regulate the voltage across the loads. But you can use this formula to calculate. This formula is sufficient to calculate the output capacitor value for the buck. So you can have these switches maybe unidirectional, maybe bidirectional. For the input to the buck, you can use this concept, the diode bridge rectifier or whatever is the modulation index. You can calculate the DC link voltage at this point. And if you assume there is a buck, you can calculate for the buck accordingly as the boost, as for the boost we did. So specifically, some conditions may be given that for this modulation index you calculate. Then accordingly, your modulation, depending on the modulation index, your DC link voltage value can change. So if I frame the problem like that, then the DC link voltage needs to be considered. And then only you can find as per the duty, operating duty of this converter, you can find the V0. But V0 was given here, that's why it became easy. You can only plug in using this formula the value of the CDC. But if I frame the problem as a two-stage problem, AC to DC and then DC to DC, you need to consider the buck converter also and then calculate for the output capacitor value. So for both the problems, yes.
Sir, the answer is coming 16.5 millifarad. By calculating, we can get 1.65 into 10 to the power minus 4. When converted to millifarad.
Let me check. 300 is the power divided by V0. V0 is what? 120.
120.
Divided by 4 pi into Fs. Fs is 50 into 2.4, right?
2.
No, I am
24.
getting 1.5 millifarads only.
Sir, 24, sir. Del V0 is 24.
No, 2.4. 2% of 120.
Okay, I'm sorry.
Oh, sorry. I wrote it like that. It appeared that 24. 2%. Okay, 2% of 120. Sorry, this should be 2.4 volts. Here.
Yes, sir.
Sir, what is only VFS, sir? VFS?
Just please repeat. Your voice was not clear.
EFS value, sir? EFS?
50 hertz. Line frequency value.
Okay.
You can use this directly to calculate the value of CDC, right? DC link capacitor I'm talking about, right? So let me be clear here. So did you understand which capacitor value we calculated here? Hello? We are calculating the DC link capacitor value, okay? Please be clear. If you are having another buck stage and then another capacitor, that is the buck capacitor for another stage. But for this problem, you are calculating this capacitor, the input to the another converter, or directly if you calculate, then the output of the VSC I can tell converter. So this is CDC, right? The DC link voltage capacitor. Just as the previous problems we did. So this is CDC, right? For that, output voltage is also this DC link voltage. Please understand clearly. DC link output, okay? And this is line frequency of the AC side, line frequency. Power frequency I can tell. Del V naught, whatever is that. Accordingly you can calculate. Okay? So I think this is okay for the converters, and we can move on to the solar and wind energy conversion systems concepts, because there may be some questions for the assignments and as well as the your exam. So first of all, let us cover the solar power conversion systems or solar microgrids. So solar microgrids are microgrids where you interface solar photovoltaic arrays which are capable of generating solar energy, and you convert that to electrical energy by using solar photovoltaic arrays, and you connect them in such a way that they can throw the power at the AC ports of the microgrid, because the AC three-phase supply is there and you have your solar photovoltaic array. So you need to do some arrangement such that you can achieve maximum out of this solar photovoltaic array and can throw that power to the grid. So you need some medium, interfacing medium, right? So who will do that? We will connect a voltage source converter, right? DC to AC, and we use some interfacing inductors, as you have seen also the topologies, and we connect them to the line. Now another concept is that you need to, this is the DC side, right? You need to impress such a voltage across the solar photovoltaic array such that it operates at its maximum power point. Because you know that whenever a solar photovoltaic array is connected to some loads, it will not necessarily operate at its maximum power point for the given radiation, right? So for each given radiation, you have some PV curves. For example, for this, then for this, then another for this. So R1, R2, R3. So for different radiances, you have different PV curves. Accordingly, your maximum power point voltage also changes. So actually, this is just that if you change the resistance across the PV, you can see the load line across the PV will declare the characteristics. And if you can make the characteristics in such a way that it forces it to be at that point for the given radiation at the maximum power point, then you are not doing nothing but playing with the load line. So your converter is actually emulating load line to achieve maximum power point transfer. To achieve MPP or maximum power point transfer, as per maximum power transfer theorem also you know that for a particular load line you can, that is for example your internal impedance is actually matching with that of the load, then only the power transfer can be maximum. Similarly, if the load line across the PV is such that your VI characteristics is intersecting with that of the PV characteristics at that point, maximum power point. So if this intersection happens at this point, then only we can tell the converter that the PV is actually operating at its maximum power point. So to take that, we are actually interfacing the converter. What the converter will do? The converter will vary the DC link voltage across the PV. So the converter is behaving as a variable resistor across the PV, a resistance with which can vary, and accordingly it will make the voltage V DC equal to the maximum power point voltage for that given radiation. Because if the radiation change, then the VMP maximum power point reference will change. So you have to control how we will generate that VMP ref from VPV and IPV. You measure VPV and IPV and pass it to some MPPT techniques where you have the perturb and observe and you have the incremental conductance algorithms. It will check by perturbing the voltage values that whether the power is increasing or decreasing. Once in steps, once it finds that point, it sticks to that point and give you the value of V ref, MPP ref. If you get that point, after you perform according switching, and by accordingly switching, you can maintain the value of VDC to that value. So who will maintain the DC link voltage? Can anyone tell me in this condition, in this configuration where we have no batteries, only the solar and the grid? Who will maintain this DC link voltage? To maintain a voltage across a capacitor, you need some power source. Who will give the power? Anyone can tell me?
Inductor.
No, where the power it will draw from? The grid, right? It will draw the power from the grid to maintain the DC link voltage using some PI loops, where the DC link voltage reference value will be coming from the MPP algorithm, such that your PV can push maximum power. Once you get that maximum power, you throw that into the grid. You also have this multifunctional ability where you can control the inverter to achieve sinusoidal grid currents, irrespective of the distortion in the connected loads that we already discussed in the DStatCom controls. Where you have loads of irregular nature, you can also embed, I can say, multifunctional controls into the converters such that you achieve maximum power point of the PV, as well as you can throw maximum power at unity power factor, I can tell, balanced grid currents where there is no harmonic distortion of the loads reflected into the grid. So you can also regulate the grid currents parallelly such that you can achieve improved power quality operation. So that is very important that you interface these renewable conversion sources using the converter, and you utilize these converters to provide also harmonic compensation for the loads such that your grid, you don't incur the grid penalties. So you must know that for rooftop arrangements of the consumers, you push power to the grid. You must know the net metering and all those things. You push power to the grid, but you should push power to the grid not at, I can say, non-unity power factor. You have to do it at unity power factor and balanced currents, irrespective that your loading may be irregular or unbalanced, or your load may be not purely resistive, that is not purely unity power factor. Irrespective of all those things, you need to push the power to the grid at unity power factor, balanced sinusoidal currents. So for that, this converter is very helpful. This converter has multifunctional operation. You must have learned the converter controls also in the DStatCom or DStatCom modules. Though those controls like ISCT, instantaneous symmetrical component theory, or IRPT, all those control techniques, DQ, SRF, you must have known these terms. These controls are used for pushing the currents and taking the maximum, and the PI loops I already told you to maintain the DC link voltage. So accordingly, you can generate the reference currents and can operate your converter in current control mode to regulate the grid current as well as operate the PV at your MPPT. So PV, if you impress the voltage, a fixed voltage, reference voltage as per the MPV voltage, PV will start giving the maximum power. The converter here is behaving as a variable register to emulate the load line, such that your load line intersects with this maximum power point and you get the maximum power transfer. So everything is operating out of maximum power transfer theorem. Only you need to understand why you are interfacing the converter. So this concept is useful for the solar photovoltaic conversion systems. So for single phase also you can do the similar things, where this side is not affected by what kind of AC configuration you are interfacing it to. This may be a 3-phase 3-wire or 3-phase 4-wire or single phase configuration. You can interface and push the power at unity power factor and sinusoidal grid currents, irrespective of the load derivatives. So that is why it is important to be discussed in the power quality perspective. So other topologies also you must have seen for solar, where you have the battery energy storage, where the battery maintains the DC link voltage. So can anyone tell me if the battery is used directly to connect it to maintain the DC link voltage of this converter? Can you achieve maximum power point tracking? Because the battery will provide fixed voltage across the PV, irrespective of any variation in irradiance. But we need variable voltages at the reference MPP points to allow the MPP operation of the PV. So is that possible if the battery is directly tied at the DC link? This configuration will work or not? Can anyone tell me? If I connect a battery at the DC link, this is the battery. Can I directly interface at the solar terminal? Will it allow me to operate the PV at MPP, maximum power
It
point?
needs a controller. It needs a controller too.
Where the controller will sit? It needs a converter, right? Between another DC-DC converter, right? Otherwise, how will you impress variable voltage across the PV depending on the radiation? The controller will operate on the converter, DC-DC converter, where you will regulate the converter control, where its output is fixed, but input is variable. Input is changing by changing the duty ratio of the DC-DC converter, which is sitting between the DC-AC and PV. The battery is maintaining the output of that converter, and the input is regulated as per the control algorithm, where the control will work as per the to generate input voltage across the PV, same as the VMP ref. So once you impress that maximum power point reference voltage across the PV for that given irradiation, then only your PV will throw the maximum power as per the variable load line. As I told you, it should emulate that particular resistance value for which I am telling it as the load line. For that particular resistance value only, that characteristic will coincide with the maximum power point, your VI characteristic. So I want that. So that converter will emulate that based on the control, and the battery is doing two things: maintaining the DC link of the DC-AC, as well as allowing some support during some. You may control the reference current such that some power is also stored into the battery, as well as during emergency times you can take the power out and utilize the stored PV power during night time. I can tell when the PV is not generating anything, you can use the battery to push the power in addition to the source or the supply to support the loads and sell some power also. You can do that. Okay. So batteries are also used, but batteries are expensive. That's why some batteryless. Mostly you will see single stage. We tell that as single stage. Okay, where you have one DC-DC converter and another DC-AC converter. That is two stage of power conversion or two-stage topology, and where you have only one DC-AC converter. So depending on the power stage, we can tell it at single stage. So single stage means only one power conversion stage. So there will be only one power conversion stage means only the DC to AC conversion stage. And here you have in two-stage power conversion, you have DC to DC, where you have the boost or any DC-DC converter plus DC to AC conversion stages. So all the renewable systems have these stages, maybe DC-DC or DC-AC. That there will be DC-DC or DC-AC, right? So these conversion stages enable more flexibility and more degrees of freedom to operate the control on the converters. And you can achieve multiple additional, I can tell, operational benefits out of them. So that way they are actually used. In application to application, the topologies will vary based on the requirements. And you have to accordingly change the control techniques also for that. The philosophies, because the philosophies will change, right? due to the additional components, whatever you want. Accordingly, you have to control the reference currents to push the power. But one thing, any topology you do, you have to abide by the grid codes. That's why power quality rules are set, standards are set by IEEE. You can see standard 519/2022, and harmonic IEC standards are also there. So those standards are set, and you have to abide by those rules, and accordingly you have to select the control, such that irrespective of load side disturbances, you can push the power or take the power from the grid at unity power factor balanced more or less sinusoidal current, and THD should be less than 5%. Those rules are there. You can just download IEEE 519 or IEC standards and can see the harmonic criteria. The harmonic content of that grid currents should be less than 5%. So accordingly, we do that. So accordingly, with battery or battery-less topologies or some single stage, two-stage topologies exist, and three-phase 3-wire, three-phase 4-wire, single-phase configurations also exist. Those are already discussed in the course. I just wanted to throw a brief light upon the controls, and we'll discuss more about it in the coming week. So we'll have some problems on them also, which we'll first go with the wind conversion system and then with the solar power conversion system, and then do some problems on them, and that will be it. Okay. So if you guys have some problem, we can just discuss, or we can end the session. If you have some problem, you can just ask. Any problem you faced in the week or some assignments, you can just ask. Or else we can just wrap up the session, right? Yes, any doubt, or you can leave. If there are any doubts, you can ask. Okay, so you can leave. Okay, I'm stopping the session. If there are no doubts, I will stop the session here. So thank you. You can leave.
Thank you, sir.